complex numbers. A long time ago, somebody needed to solve that equation. X squared plus 1 equals 0. Pretty simple looking little equation. That equation has a big problem. What's the big problem with that equation? That's the same as x squared equals negative 1. If I put a real number into here and I square it, I never get a negative answer. I might get 0. But even if I plug in like negative 1, if I plug in negative 1, what's negative 1 squared? Positive 1. So this equation has no real answer. What do we do when an equation has no real answer? Right, just like when you were a kid and you didn't have any real friends. You make up imaginary friends. When equations don't have any real numbers, we make up imaginary answers. When you were a kid. Just trying to give you the benefit of the doubt. So, we develop imaginary answers. So we're going to set J equal to the square root of negative 1. Now, if you've had math classes before and you've talked about imaginary numbers or complex numbers, they probably use the letter I for imaginary numbers. We use the letter J in this class, and we have a reason. We'll get to that reason in just a few minutes here. I can be confused with, oh no, because see, when you write an I is written this way, you see with a little tail, and then you can't confuse it. That's right. So normally in most math classes we use the letter I because I stands for imaginary. In this class we're going to use J. And again, like I say, we have a reason. And we'll get to that before the end of the day here. We'll talk about why we use J instead of I. All right, what this allows us to do is this allows us to write things that we couldn't write before. For example, the square root of negative 4. What I'm going to do with the square root of negative 4 is I'm going to write it as the square root of 4 times negative 1. Because the square root of 4 is a real nice number. What's the square root of 4? 2. What's the square root of negative 1? Square root of negative 1 is not a real number, it's an imaginary number. That's a J. And I could do the same with square root of negative 36. What's the square root of negative 36? (6j), because negative 36 is 36 times negative 1. Square root of 36 is 6. Square root of negative 1 is j. Alright, so let's look at this handout that I gave you here. In the handout, we define j as the square root of negative 1, and we use that multiplication property like I just had been doing. We already did this one. Square root of negative 4 is 2j. What would be negative square root of negative 25? All right, so the two negatives just don't reduce each other out. That's correct. So what you have to do is deal with inside the square root first. The square root of negative 25 gives you a 5j, and then you have that minus still sitting on the outside. So you're absolutely right. This is minus 5j. How about the square root of negative 12? Close. Not 6j, but you're close. You're very, very close. What you're doing is you're saying negative 12 happens to be 4 times 3 times negative 1. The square root of 4 is a nice number. The square root of 4 is 2. Is the square root of 3 a nice number? No, so we're not going to be able to do anything with that. That one's going to be left as square root of 3. And then the square root of negative 1? J. Alright, so typically we would write that as 2j square root of 3. The traditional thing is to put the square root thing last. Why should we put the square root thing last? Correct. If I don't put the square root last, then there could be questions as to, is this j under the square root or not under the square root? And you'll notice what I did, this is what I had to do when I was learning about square roots, is I had to put a little tail on my square root to clearly indicate that that's where it ended. So when I was in school, if we did not put the square root last, we had to put a little tail like that to say, this is where my square root is ending, to be very clear that the j is not under there. And if I did not put that little tail, it was marked wrong, even if it was right. And again, I wrote my I, when I wrote I a minute ago, I wrote I like that. We had to write I like that. And just out of, beat into me enough times, I still write my I's like that instead of like this, because then it is confusing, is that a 1 or an I, especially if the dot isn't very well known. All right. A complex number is a combination of a real number and an imaginary number. For example, 3 plus 2j is a complex number, since it is a combination of the real number 3 and the imaginary 2j. A complex number in the form a plus bj is said to be in rectangular form, where a is the real part and b is the imaginary part. Alright, so let's talk about some complex numbers here. So for example, I might give you 5 plus the square root of negative 16. Is that a complex number? Yes, because it could be written as 5 plus 4j. So that's a complex number. What's the real part? 5. What's the complex part? 4j. How about square root of negative 100? That's 10j. Okay. Is that a complex number? No, why not? Doesn't have a real part? All right, so it should be a real number, like this one, plus something with a j. So is this one complex? No? What if I were to write it as 0 plus 10j? Is that the same thing? Yeah, so is it complex? It is complex. It's a trick question. It's a trick question. What's the real part? The real part is 0. What's the complex part? 10j. So that is a complex number. The real part just happens to be 0. 7. Is 7 a complex number?
Yes.
Yes. How come? It is prime. That doesn't have anything to do with the answer, though. Well, because I tricked you on the last one, so it seems like I'm probably going to try to trick you again. Does it have a real part? Yeah, it has a real part, 7. Does it have a complex part? It does?
It's the square root.
No, you're working way too hard. This is 7 plus 0j. So, does it have a real part? Yeah, it does. 7. Does it have a complex part? Yeah, once again, it's 0.
So
Yeah.
now all numbers are complex.
So all numbers are complex numbers. That is correct. That is a correct statement. All numbers are complex numbers. Okay, so the point is that all numbers are complex numbers. Some of them are real, which is more important, like the number 7 happens to be a real number, but a real number is also a complex number. All right, so where complex numbers show up for life in general happens to be in electricity. And I'm going to be honest, I don't know a whole heck of a lot about electricity, other than I'm pretty good at turning the light on, turning it back off. I know how to do that. But here's some things I found in your book here. It says, in electricity, the impedance Z of a circuit can be represented with a complex number. The impedance in each branch of a series parallel AC circuit is given by Z equals R plus XL minus XC times J, where R is the resistance, XL is the inductance reactance, and XC is the capacitance reactance. Determine the complex number that represents each branch of impedance Z1 and Z2 for the circuit below. All right, so we have two different circuits here. I guess I got to stand and block the sun. So we have this circuit. There's one circuit. And then we have, not one circuit, one branch, I mean. And then we have another branch going all the way around here.
So the circuit is unequal.
It does look like it's broken right here too, on mine. It's not supposed to be. It's supposed to be a complete circuit. I agree. I'm not sure what happened when I copied that. Please don't show up. Okay, so determine the complex number that represents the branch impedance Z1 and Z2. So Z1 is going to be the green one. So in Z1, what's the resistance? R is 6. Plus, XL is 3, and there's no XC in that circuit, is there? In that branch. So that's just going to be 3J, 6 plus 3J. How about in Z2? Z2 is the black one. R is 4. And XL minus XC. No XL. So it's 0 minus 5. So 4 minus 5J. Alright, so just a few minutes ago here on the other side of this page, it said that a complex number written in the form A plus BJ is said to be in rectangular form. We take things that are in rectangular form and we graph them on something called the rectangular plane. And the rectangular plane looks just like this. So it says, complex numbers are represented in a two-dimensional plane called the complex plane. The complex plane, which is shown below, is formed by intersecting a horizontal real axis. So here's the real axis, with a vertical imaginary axis. Plot the branch impedance Z1 and Z2 in the complex plane below. So how would I graph 6 plus 3i? Well, the real part is 6, so I'd start at the origin and I would go to the real part, which is 6. And then the complex part is 3, so I would go up 3. And these are quite often represented as vectors. So we would write 6 plus 3j. All right, so does anybody know why we use the letter J here instead of the letter I? Doesn't stand for 2. Back in, I haven't taught Math 1230 in a long, long, long time. Back in Math 1230, you talked about vectors, correct?
Yeah.
Did you write vectors in the IJ form? So quite often when we draw vectors, I might give you 3I plus 4j. I give you that vector. And that vector would be, the I direction is this way, the j direction is that way. So that would be 3 over and 4 up. 3I plus 4j. So this is why we're using j for imaginary, because j is up in the traditional vector notation. So that would be the vector 3I plus 4j. That's why we're using j's here instead of i's, because j, when you write vector notation, j is up. So it would be confusing to use I to have I be up here, but I be to the right there. Confusing notation. Anyway, there's 6 plus 3i. Where's 4 minus 5i? Or, I'm sorry, I'm so used to using i's. 4 minus 5j. 4 minus 5j would be right there. 4 minus 5j would be right there. This is 6 plus 3i. In electricity, complex numbers are thought of as vectors. These vectors are called phasors. And so I already drew our two complex numbers as vectors, or more importantly, as phasors. There they are. Placing the tails at the origin, draw vectors z1 and z2 in the complex plane. We already did that. The magnitude of each impedance vector is the vector's length. Using the Pythagorean theorem, find the magnitude of z1 and z2. What's that mean? Yeah, basically what they're saying is, for this vector here, how long is it? The magnitude is the distance from here to there. And they say use the Pythagorean theorem because we can just draw this triangle. This length is 6, and this length is 3. It's just 3 spots up. So we can go ahead and we can use the Pythagorean theorem and we can find the length of that vector. So the length of that one, so z1 is the square root of 6 squared plus 3 squared, which is the square root of 45. And usually magnitude, the symbol for magnitude is usually that. It looks like absolute values, but we use double brackets instead. So that usually stands for magnitude or length. The symbol is magnitude, which is a fancy word for length. Or distance is also a fancy word for distance, correct. All right, then it says find the magnitude of z2, because it would be square root of 4 squared and 5 squared, because it would be 4 in this direction, 5 in that direction. Square root of 41, 16 plus 25. The direction of each impedance vector is given by the phase angle, which is the standard position angle of the vectors. Use right triangle trigonometry to find the phase angle for z1 and z2. All right, so back in the picture, what they're talking about is the phase angle for z1 would be that angle right there. How can I use right triangle trigonometry to find that angle? Tangent would be the easiest one because I know the opposite. I know the adjacent. So that would be tangent theta equals 1/2, or theta is tangent inverse of 1/2. Or maybe you call it arctangent of a half. What's the arctangent of a half? It's something. It's not a special angle that I'm aware of, so we're going to type that into our calculator. We're going to make sure our calculator is in degrees mode. We'll give the answer in degrees. What'd you get? How much? 26.6 degrees. Same exact thing for Z2. For Z2, our phase angle is this angle right here. Again, I know the opposite is -5, and I know the adjacent is 4. So tangent of this angle, I'll call this one alpha. Tangent of alpha is, what did I just say it was? I forgot already. -5 over 4. So again, theta is tan inverse of -5/4. And again, we grab our calculator. Calculator says, I don't care. I like negative numbers. -51.34 degrees. So yeah, you can give the answer in negative as far as I'm concerned. If somebody was picky and wanted the positive answer, what would you do? Add 360 to it, or subtract that from 360. Same thing. Correct. All right. So the last thing we talk about is using the magnitude r and the phase angle theta. Write each impedance in polar form. So rectangular form was this 6 plus 3j. This was rectangular form. Why is it called rectangular form? Yeah, because we're dealing with a rectangle. We're going right and up. Basically, you draw a rectangle, don't you? In polar form, we write the r value. The r value we found was square root of 45. And then we write this symbol. Looks kind of like a less than symbol, except the bottom is parallel to the bottom of the paper. And then we give the angle. 26.6 degrees. So that's called polar form. Where, what's this first number again? The magnitude, which is the distance from the origin. And this angle is theta, is the phase angle. All right, so there's Z1. And then Z2 was 4 minus 5j. Again, that would be our rectangular form. Our polar form would be square root of 41, angle of negative 51.34. Yes, because if you don't put the degree symbol, it means you're working in radians. So yes, we should put the degree symbol. All right, so let's do a couple more of those, converting them into polar form. Give me a point, give me a vector, a complex vector, in rectangular form that lives over here in quadrant number 3. -5, -5 plus 6j. All right, so -5 plus 6j, that would be here. -5 plus 6j. All right, so there's that vector. That's supposed to be a solid straight line there. There's that vector in rectangular form. I want you to convert that into polar form for me. Well, what do you have to do to convert it into polar form? You got to find the magnitude. How do you find the magnitude? Pythagorean theorem. The magnitude is quite often called r. And there's actually a little formula for it. We're using Pythagorean theorems. It's going to have a square root, right? It's really just a distance formula. And we know that this distance is 5. And we know this distance is 6. So the formula for r is really you just take the real number and you square it, and then you take the complex number and you square it. Not much to it. That's 25 plus 36, square root of 61. All right, how about the angle? Tangent of theta is the y over the x, so it's 6 over negative 5, which means theta is tangent inverse of negative 6/5. And you use your calculator. Your calculator said 129.8? Alright, so I wanted that answer, because the calculator doesn't give you the right answer. The calculator gives you, what did you say it was, negative 50.19 degrees. And you need to recognize that that's not the right answer. Well, the problem is, where is the angle negative 50.19 degrees? Yeah, what they've really given you is that angle right there. So when you use that tangent inverse button on your calculator, it's always going to give you an answer that's either negative and in quadrant 4, or it's going to give you a positive answer in quadrant 1. If your original vector is in quadrant 2 or quadrant 3, you've got to fix the angle. And how do we fix it? We subtract it from 180, or take the angle it gave us and add 180, same thing. So in this case, to get the right angle, we have to add 180 degrees. So watch out for that. If you're in the second quadrant or third quadrant, you're going to push the buttons on your calculator, you're then always going to have to add 180 degrees. So 129.81 degrees is the right answer. All right, so our answer in polar form would be square root of 61. Ooh, that's not a very good sign. Close enough. 129.81 degrees. Questions on that? Why do we write our complex numbers in polar form? So we know the length and the angle. Okay, that's true. It also turns out, as we will see on Monday, that doing arithmetic, like multiplying and dividing in polar form, is very, very easy. So that's what we'll deal with on Monday. Why do we write it in polar form? There's a good reason for it. And we'll do that on Monday.